Okay, so let's start. You can hear me up there? Okay. Okay, before we get to what we want to talk about, homework 1 is 1. I hope all of you know. All of you looked at it, started working on it. I know that there have been some questions already, so which is a good sign. Please go to the office hours. You have plenty of office hours every day of the week. Please go to the recitations, ask questions. Any questions now? No questions. Questions about stuff we've done last time? I always get really good questions in the office hours, and for some reason, you're too quiet here. Okay. Recall the late policy. So please don't send me email, tell me that you're busy for some reason. Everyone is busy for many reasons. So that's why we have the late policy, and we try to make it uniform. So you get to decide when you are busy. And I think it's, given that we only have 5 problem sets, this policy is good enough. So no need to ask for additional time. Just use it if you need it. My recommendation is don't use it now. Try to defer it to the end of the semester where you're going to be even busier and some surprises might happen. Piazza. So you ask good questions on Piazza. Would be nice if you also answer these questions, or at least some of you. For 2 reasons. First, it's a good exercise, and we're going to reward people that are highly active. We'll figure out the details of that later, but if you answer a lot, we keep track of it, you'll gain something from it. 2, it helps us to understand what people do understand and don't understand. So be active. Questions? Okay, so let's move on. We started to talk about it last time, kind of a detour from learning algorithms. It's going to be a short detour, just to talk a little bit about how do we evaluate what we're doing. Metrics, methodologies, a little bit about statistical significance. So that's the game we're playing, right? So we think about batch machine learning. We're given data, training data that we use to train the model, pairs X, Y. And then we want to apply this model to new data to make predictions. And basically, we want to ask the questions of how well are we doing, right? So is this model good? And we need to do at least 2 things. We need to understand how to measure the performance of the algorithm. And 2, we need to know whether it's good. So, okay, you train a model, maybe a very simple model. Typically, when we run experiments, we always want to start with a straw man, with a very simple baseline. Are you doing better than the baseline? So we need to be able to compare algorithms and decide which one is better, or whether one is better than the other, or maybe they are basically equivalent. So that's what we want to talk about. So we started last time, and I'm going to just run through it to talk about a few things. One is the issue of splitting the data. Training data, test data, on which you're going to report your performance, and the need to have a development set to guide you in developing your algorithms, sometimes in tuning your algorithms, and so on. So that's one parameter. The second thing is how to measure performance. So we talked about accuracy last time. We then moved from accuracy to talk about recall and precision. And we showed this nice figure that explains what we mean by recall and precision. And we justified it in the context of an imbalanced data set. where 95, 99, 99.9% of your data is actually negative, and just measuring accuracy is not going to give you an indication of whether you're doing well or not. Similar issues arise when you do more than binary classification, multi-class classification, so we talked a little bit about that. We then talked about, and this is just, we also talked about the notion of confusion matrix, which is another way of looking at the same thing. I defined recall and precision as a function of these numbers that you see in the confusion matrix. Okay. The last thing I think we said is that we often want to look at recall and precision together, because really, if you have very high recall, you will typically have low precision, and vice versa. You want to think about what is the best way, given your application, for example, to trade off this. Maybe you really care about high precision, and it's okay to have low recall. Maybe you have an application where you really care about recall because you're going to present information to people, and you count on them being able to filter this very quickly, but you want at least to give them an idea of what's in the data. So high recall is more important to you than high precision. So you want to be able to trade off these things, and this recall precision curve is a tool for doing it. You can also just take specific statistics from this recall precision curve, and one of them is the F measure that is essentially a weighted harmonic mean of precision and recall. And you're going to use these metrics as we go in the experimental data sets. Okay, so one of the things that we want to be able to do is, once we know how to measure performance, accuracy, F1, whatever you prefer, we want to be able to compare two classifiers. And I'm going to run through a few important thoughts about doing it. Frankly, this is the most boring part of the class, so I'm going to run through it quickly. It's basically a recipe of what you need to do. I'll justify at least some of these things, and then we're going to move on to more interesting things. But really, this is important. So one question that hopefully you can answer easily now is, if we want to compare two classifiers, can we use the training accuracy to choose between them? Why? Answer is no. Yeah. Yeah, it's very easy in most cases to get good results on the training data, and that may not be a good indication for how well you will do on future data that you've never seen and you really care about. So clearly no. How about accuracy on the test data? Why not?
Because accuracy may not be the best measure of its performance.
Okay. Any other metric on the test data? Yes? Okay, so why? I can't hear you.
You'll fit on the test data then, which you're not supposed to do, because then you're going to
Right, so we don't want to use test data as part of our development process. And basically look at the test data, say, we're not happy, let's do a little bit more, look again at the test data, you're not happy, let's do a little bit more, maybe let's change our features, and so on. That you don't want to do. That's why we have development set. But let's assume you're done with the process. You're happy, fixed models, C1 and C2. Can you now use the performance on the test data as a way to tell you whether C1 is better than C2, whether C1 and C2 are essentially equivalent? So one objection here is a valid one. Maybe accuracy isn't the right statistics. But let's assume we figured out the right statistics. So I'm going to replace accuracy with F1. Is that okay now? Yes.
Yeah, it should be okay, because that's probably what the test data is for.
So in principle, it's okay. You know, that's what we want, right? So the answer is, my answer is yes, but. And the but is that it's one number. And really what you want is you want to be able to get some more statistical confidence that, yes, I got for C1 a higher number than for C2. Does it mean that every test data that I will look at, it will behave this way? So I want to be able to get some statistical confidence that what I see here, these two numbers, comparing them, is really something that I'm going to see with high probability whenever I do this. And that's basically what we want to do, what we want to talk about. How do we get it? So the basic methodology that we're going to talk about is that of cross validation, because that's the most common and simple way to deal with this thing. So basically, instead of a single training set, we're going to split the data to folds. For example, if we split it to n equal size parts, think about n as 5. That means that you use 80% of the data for training, 20% for test, and you repeat this 5 times. So you train and tested 5 different classifiers, and now you have more than one single number. At least you have 5 numbers, and you can take statistics over them. And rather than a single accuracy or a single F1, now you have an average plus standard deviation. You know something about what's happening. So this would be the process that you'll have. The red thing is going to be your test data. You have 5 different test data. And the rest is the training data. That's what, and in fact, this is the process that you're going to run also in your problem set. So let's just take a concrete example. In this case, I drew threefold. So you have 3 test data that you're sampling from the data, and then you can measure performance on each one of them and take some statistics. That's basically the process. So really, cross-validation generates an approximate estimate for how well you will do on unseen data, because you're sampling and you're going to do this many times. As k approaches n, of course, your model is going to be better because you trained on more data. On the other hand, it's going to become more expensive because you have to run this many, many times. In the limit, where k is equal n, this procedure is called leave one out. It basically says, I'm going to train on all the data that I have but one example, test my performance on this example, and I'm going to do this n time, where n is the number of examples I have. Sometimes this is done when you don't have a lot of data, but in principle, choosing k that is smaller than n is a compromise. People have done a lot of statistical research on this, and for some reason, the recommendation is to use k equal 5, 5-fold cross-validation, and this is something that is typically used in the literature. Okay, so basically the idea is robustness, right? So we want to be able to be more robust. Now you can do this repeatedly. You can do many, many times cross-validation. So you imagine that you have T trials, you randomize the data set, you do k-fold cross-validation, you do it again and again, and now you have T times k test performances, and this is something that will allow you perhaps to get even more robust statistics on the data. You can draw learning curves if you want, and you can do additional sort of statistics on the data. So in our case, in most cases, we're going to do just one cross-validation. This is going to be enough. Okay. So what are we doing once we've done this cross-validation? Basically, now we want to understand which algorithm is better. So let's assume you have two classifiers, A and B. You train and test them on the n-fold cross-validation. For each fold, you measure the accuracy. You could replace the accuracy here with F1, with F0.5, with any other way that you decided measuring the performance is best. And then you look at the difference. And the question, is this difference significant? That's the key question that we have. Is algorithm A better than algorithm B? Yes or no? So basically, in the next few slides, I'm going to talk a little bit about the methodology that we're going to use in order to answer this question. Basically, can we distinguish these models? And if so, which one is better? So the methodology is called hypothesis testing. I assume some of you have seen it in statistics classes. Basically, we want to know whether a hypothesis is true given the data. We're going to make a hypothesis. It's going to be called the null hypothesis. We want to know whether A is different than B. So the null hypothesis is going to be no, A and B are identical. Now let's collect data and see whether this null hypothesis holds or not. So basically what we want to do is we want to induce a distribution over some statistics, and as a function of this distribution over the difference, for example, between the performance of A and B, decide whether we can reject the null hypothesis or it's true. Whether it's true that A and B are statistically the same or whether they're different. So we define a distribution. It's going to be a fixed distribution for our purpose over some statistics. For example, the difference in accuracies. We're going to select a level of significance that we care about, which basically is going to, you can understand as with probability at least 95%, I'm sure that the null hypothesis is wrong, or with probability at least 99%, I'm sure that this null hypothesis is wrong. And this will allow us to determine whether we can reject this null hypothesis with this confidence. So basically, it's a methodology that results in a very simple procedure, compute some statistics over the data, look at a table that belongs to the probability distribution that you believe these statistics satisfies, and just decide if you're confident enough at the level S and you can refute the hypothesis or not. So we typically use, in these cases, what is called the pair t-test. Basically, the pair t-test is a statistics that is used to compare two population means when you have two samples and you can pair them, which is the case that we're going to have now. We have 5-fold or n-fold. From each one of the folds, we have two statistics. The mean, the performance of algorithm A, the performance of algorithm B. We can pair them, and therefore we're going to use this statistics. So again, the null hypothesis, for example, is going to be there's no difference between A and B. The expected accuracy are the same. So the null hypothesis specifically is the expectation of P of D is 0. And we're going to use the n-fold cross-validation to estimate this P of D, basically averaging 5 numbers if n is equal 5, computing the standard deviation of these 5 measurements, and feed it into a formula that I'm indicating here, also written in your homework. And I'm pretty sure that we also referred you to a table where you can read off the t-distribution form. So in this case, S is going to be the standard deviation of these measurements. M is going to be the mean. And N is going to be the number of folds. Capital N is the number of folds, and that's going to give you the statistics. basically that's it. So here is the flow. Compute the difference between the two observations on each pair, compute the mean difference, compute the standard deviation, calculate the error, and compute the t-statistics. Now, there is a lot behind this to try to justify that this is the right distribution to look at, and some theory that has to do with what is the right n, capital N, what is the number of folds, and so on. We're not going to dwell on this. Basically, think about it as just a procedure that allows you to get some confidence in the comparison that you're making. Now, it's not the only way to do it, and I'm going to hint on one other statistic or one other approach to doing it, and there are many others. Another one is something that we call McNamara test. In fact, let me go here because this is where it's clearer. So basically an alternative to cross-validation where you actually have explicit predictions of examples. In cross-validation, you actually didn't care about it. You only cared about performance on each one of the folds. If you have access to the model itself and you can run it on a set of examples, you can use the McNamara test. Basically, McNamara test says, let's look at this 2x2 contingency matrix. Look at examples that are misclassified by both algorithms. I'm going to call it here N00. Examples that are misclassified by A, but not by B, N01. And the bottom line, example misclassified by B, but not by A, N10. An example that both algorithms got right, N11. So once we look at this, of course, the sum of all this is the total number of examples. Then McNamara test provides a way to get some statistical measure of how different or whether A and B are different. Essentially, we start again with an hypothesis that the two learning algorithms have the same error rate on a randomly drawn example. So N10 is equal to N01. And we compute these statistics, N01 minus N10, the difference between these two, square divided by N01 plus N10. And these statistics can be shown to be distributed, again, as a t-distribution with 1 degree of freedom. So you compute this, go again to the t-distribution table, and look at it and see whether the number that you got is statistically significant at the whatever you care, 5% confidence, 1% confidence, and so on. So the difference between these two, the procedure is very, very similar, and the distributions of these statistics are similar. The difference is what do you have to play with. Sometimes all you have is performance of algorithms. Sometimes, and you cannot even compute this N10 and N01 because no one gave you performance on specific examples. Sometimes you do have access to this, and then you can compute McNamara test. And there are other tests, but for us, this is going to be sufficient at this point. Questions? Yeah.
Just as a point of organization, when you're doing k-fold cross-validation, you train k models, or I guess in this it's n models.
Yes.
So you have your n models, and you're measuring the error rates that each model has, and you're sort of computing statistics around those error rates. When you want like a final model, do you then basically just these statistics and you're going to retrain the model on the whole data set? Or do you somehow average the models together that you train on the k-fold?
Okay, good question. So first of all, the question is what is your goal here? If you're doing homework, basically all we cared about is the statistics over the 5 models. We don't care about producing one final model. If you're going to work in the real world, it's going to be algorithmic dependent which model do you want to do. Eventually, you may want to say, I don't have a lot of data. Now that I've done this 5-fold cross-validation or 10-fold cross-validation or leave one out, I'm pretty confident that my model makes sense. I'm going to now turn it on all the data I have and launch this model, which is the typical way people are going to work when they don't have a lot of data. Now, whether you want to average models or not really depends on the learning algorithm. Quite often, averaging model or combining model one way or another, not necessarily uniform averaging, is a good thing to do. As you will see in the homework and you'll see later in the semester. But this is really specific to the learning algorithm that you have. So this is called an ensemble, and typically it's a good thing to do. Other questions? Yeah.
So in the Pierce t-test, you mentioned we should also compute the error of the mean difference. What do you mean by that?
The error of the mean difference?
I think it's the next thing.
No, that's what you do. You just compute the average of the difference between the algorithm, the performance of the algorithms. I'm not sure what you mean by the error of the mean difference.
If you go to next.
The mean difference, that's what you compute.
The fourth step, you said calculate the error of the mean difference.
Okay, okay, I see. So what I meant here is basically compute this term over there, the square root n m over s. Yeah, okay. I'll change this. Thanks. Yes?
Can you go to the McNamara test? The previous slide. Take that how the summation of these examples is coming as test, total number of test examples. But there might be some intersections as well.
No, I think these are disjoint, right? An example, these 4 cells are disjoint, right? I hope. So that's the sum is the size of the test set. Okay? You convinced it's disjoint? Yeah. Okay. Okay, so basically that's it. As I said, it's a very technical session, but we have to know something about it. And I want to move on to what do we want to do next? Okay, so next we're going to move to a new set of learning algorithms, which actually is going to be is going to carry us one way or another throughout a lot of the semester. And just to give some kind of a guide for what we're going to do. So we already talked about 2 learning algorithms, or 3 learning algorithms, stochastic gradient descent. We talked about it in the context of one loss function, but hopefully you get the idea that you can change the loss function, run exactly the same algorithm, you're going to get different behavior. We talked about decision trees. We talked a little bit about the importance of hypothesis space or the importance of representation. This is something that is going to come back to us a few times. And we started talking a little bit about how are we doing, or how are our learning algorithms doing. So basically we quantify things in terms of number of mistakes we've made, or cumulative number of mistakes we've made. And one thing that we noted is in all cases, the algorithms were driven by different metrics than the one we care about. So if you think about stochastic gradient descent or gradient descent, let's assume that we care about how many mistakes we're going to make. This was not the loss that drove the algorithm. In decision trees, again, let's assume that we care about the number of mistakes. This was not the measure that drove the algorithm, right? We kind of imagine some heuristics, and we use this to guide the search for the best decision trees among all decision trees in the world. And we're hoping that eventually we're going to get to this minimal or something close to it number of mistakes. So this is something that is good to keep in mind. We're going to change a little bit and be a little bit closer to what we care about. And we're going to do this in the context of many or multiple versions of perceptrons. So perceptron is going to be a basic building block. It's a basic learning algorithm. We're going to talk a lot about it. That was actually introduced first time in this name, at least, in the 50s, 1950s. But some versions of it existed before. And what we're doing today in machine learning, to a large extent, is also versions of this. One question that we can ask as a way to motivate looking at versions of perceptron is how to deal better with large feature space, how to deal better with sparsity in the feature space. We're going to define this. And we're going to talk about various versions that deal perhaps better with overfitting. We will see that, in fact, we're going back to gradient descent, even though the first view of the algorithm may look different. And then we're going to talk about dual representation kernels, moving to multi-layer perceptron or neural networks, and move forward from there. So that's kind of the general guide for the next couple of weeks. Today I want to start with a slightly more general perspective and think about learning protocols. So for one reason or another, we are always thinking about learning, or the community thinks today mostly about learning as the following process. Someone gives you a bunch of examples. I don't know where they are coming from. You bring an algorithm. You run the algorithm on the bunch of examples. You get a model. You're happy. It's not the only way to think about learning. And I want to motivate some of these ideas because basically things are changing and are going to change in terms of our way of thinking about learning protocols. So one way to drive our thinking for the next few minutes is thinking about quantifying performance. So we want to be able to say something rigorous about the performance of the learning algorithm. What does that mean? This could mean the number of examples that we need to see before we are happy with the performance of the learning algorithm, right? So one way is to just learn on as much data as you can or have, and then look at the number and say, yes, it's good for me. Another is to be able to quantify and say, I don't need more than 1,000 examples, or I need a lot more than 1,000 examples, for my learning algorithm to do well. So the question is, can we quantify? So we're going to play the following game. We're going to learn a relatively simple hypothesis class. It's going to be conjunctions. What is a conjunction? It's this and this and this and this and this and this. If a subset of the features all together are on, I'm going to say yes. So let's imagine that we have a hidden conjunction. I'm not going to use negations here. So I'm going to call it a monotone conjunction, just to simplify things. And I'm going to tell you what the hidden conjunction is, but the learning algorithm does not know that. So the learning conjunction is over 100 variables, and it's x2 and x3 and x4 and x5 and x100. So the question is, how many examples do I need to see in order to learn this conjunction? And of course, how do I learn this conjunction?
Does the learning algorithm know that it will be a conjunction?
Okay, good question. Does the learning algorithm know that it's going to be a conjunction? In fact, it's going to know even that, for the exercise here, it's even going to know that it's a monotone conjunction. So is the question well defined? Is it clear? I have a hidden function. I told you the family of the functions. It's a conjunction. It's a monotone conjunction. How many examples do I need? And how should we do it? Is it well defined? Yes, no? Can you try to answer it somehow?
Something on the order of 2:95 examples.
Why?
So I'm basically thinking that it needs to know that 95 of the variables don't matter really. So if it sees that those 95 variables take all the 0 and 1 values and the answer doesn't really change, then it will have an idea of.
Okay, so there is a suggestion for the number of examples, but without kind of determining whether this is a reasonable number or not, I'm first going to argue that you are very biased and this problem is ill-defined. Because I didn't even define what is the learning protocol. Right? So you're biased, you're thinking about a specific learning protocol. I assume that the majority of you are thinking about the same learning protocol, but maybe not. But I had to define it. You should have complained, well, there are many ways to learn. Protocol 1, the learner proposes instances as queries to the teacher. So I'm the teacher here. I know the hidden function, you don't. And the way you're going to learn this is by asking me questions. That's a legitimate learning protocol, right? I mean, you're doing it all the time. I hope. Here's another protocol. 2, the teacher, that again knows the hidden function, gives you examples. Not the same thing. What's the difference between 1 and 2?
One, you can guide the search yourself based on what you don't know, whereas with 2, you kind of need to wait until that is just naturally covered by the teacher.
Okay.
The information is being like either asked for or given by, in one case, by someone that doesn't know the true form, versus in the second case where they do know the actual function.
So the selection of the queries in protocol 1 could be, at least at the beginning, completely random, because the learner, you, have no clue what the hidden function is, while the teacher in 2, they know what the function is, so they maybe could be a little bit more specific. So what are your expectations between 1 and 2? In terms of number of examples?
The teacher is nice, and 2 is not.
Okay, if the teacher is nice, then 2 is going to be much faster. And 3 is, I bet, the protocol you had in mind, which is there is some random source, nature, let's call it, that generated some examples. I have no idea how. And the teacher provides the label, because the teacher knows the hidden function. And then the learner is looking at these random examples with the labels and try to hypothesize or learn the function. Again, a very, very different protocol, right? Yes?
But given that the learner knows so much about the fact that you have 100 x's and the fact that it's a monotone conjunction, it would start off as random, but then you could conceive of like a way of building an algorithm where
Perhaps, so we're going to play this game now, and we'll see to what extent you're right, and whether this intuition is correct. I want to say one other thing. So I know that protocol 3 is the one that you had in mind, or many of you had in mind, definitely people that have read papers or have seen what's happening in the literature. I want to say that hopefully your generation of machine learners will deal a lot more with protocol 1, protocol 2, and maybe other protocols that you'll invent as a way to do learning. Protocol 3 is very, very restricted, requires a lot more examples than protocol 1 and 2, as we will see, and in many situations is completely unrealistic. Nevertheless, it's the easiest to study theoretically, and it's the easiest to basically develop protocols because there's no human involvement there, or less human involvement, and that's why the machine learning community has kind of opted to go this way. There are a few other reasons for that, but it's not necessarily the one that in real life you want to use. So, yes?
The difference between protocol 2 and 3 is that the source knows F in the second protocol and it doesn't know it in the third protocol. Is that it?
Well, in the third, not only it doesn't know, the examples have nothing to do with the function, potentially. Right? So they're just examples. You just wander around the room and you look at chairs, and that's it. I mean, you don't know what is the hidden function. Maybe the hidden function is going to be the colors of the chairs, or could be something completely different.
It seems like the first and second protocol assume there's someone who knows what this function is. Is that ever really the case?
Good question. What do you think?
It doesn't seem like we really run into any of those examples, and I feel like if someone knew the function, then it would be kind of contrived to try and estimate it anyway.
So I think in many, many realistic situations, when you learn something, it's basically known, or at least there's a good approximation of what you're going to learn.
Are you speaking like a classroom setting or like machine learning? Or just
And any natural setting that you have. Now, the question is whether you can probe this in the good way, just like here I kind of simplify the probing with inventing this notion of a teacher. Sometimes the teacher is not a person that stands in front of you, but some other source that can articulate or provide information about the hidden function. Here I abstracted it to be something that is called teacher, but in many realistic situations it would be something else that supplies good evidence or good information about the function. So let's just play this game. Protocol 1. The learner proposes instances as queries to the teachers. How would you go about it? What would you do? You are the learner now, and yes?
Since I don't know anything about the function, I just propose a random one that fits the constraints.
Okay. So propose a random example.
All zeros.
All zeros. And then the label comes in, and the label is 0. Next. Okay, x1 equal 1, and the rest is 0.
No. All ones. You get 1. You give me 1, then I'll remove x1 as a 0.
Okay, so excellent. So with everything that you said so far, let me just summarize. So the all 0 was a good guess to start with, but what is the but with the all zeros example?
You already know the answer.
You knew the answer. What is the answer? Has to be 0 because I told you it's a monotone conjunction. The 1 is a good example. The 1, all zeros. You almost know the answer. When don't you know the answer to this?
The answer is x1. Just x1.
If the function, the hidden function, is x1, and that's it, it's going to be positive. In all other cases, it's going to be negative. So you almost knew the answer. So let's start with an example where, it's going to give us a little bit more information. Yes?
Half of that is 1.
Yeah, this could also work, but I'm going to go with this one because it's simpler. which means I'm going to make sure that, in fact, I don't necessarily have to start with your example, which is, you said, let's choose everything to be on. What will that give me? This will give me 1 because I promise you that what I'm doing here is non-trivial, right? So there is some hidden conjunction here. And now you have to start searching for it. So the start searching means let's start dropping things. So basically dropping things means asking a question. If I dropped x100 from 1 to 0, it's as if I'm asking, is x100 in the conjunction? Everyone agrees? If I'm asking, is x99, or to ask whether x99 is in, I'm going to drop x99, leave the rest on, and so on. And basically, as a teacher, I'm going to answer to you, yes, no, no, yes, no, no. At some point, we're going to get there. How many questions do you need to ask this way? Really, you need 100 queries because you're going to ask a question about each one of the variables. And the output is going to be exactly the function that is hidden. I'm emphasizing exactly here because it's important. It's exact learning, not always something that is possible in real life. Okay, so that's what we learned. Protocol 2. Okay, so you can ask yourself the question of what if the conjunction were not known to be monotone? It's a non-trivial question. You have to really think about it. I'm not going to dwell on it now, but basically a puzzle. Protocol 2. The teacher who knows F provides training examples. So what are you going to do here? So now you are the teacher, and you are providing your neighbor information. Now, there are 2 issues here. One is what information are you going to give them? You can, tell them something. We're going to restrict the channel between the teacher and the learner to be examples. Why? Just because I want to put everything on a relatively equal grounds, so we can count examples. But notice that it's not necessarily the only way to interact, right? Via examples. Maybe there are, wider bandwidth channels that you can pass information. But let's do examples. So what would you do?
So I know the variables which are involved. I'll make them 0 and everything else 1. And so 1 by 1. For example, if I knew that x100 is involved in the consumption, then I give all ones x100 0 as one of the examples. So it will basically tell the student that x100 is a part of the consumption.
Okay, so basically what you want to say, I want to tell them that x100, let's say, is in the conjunction. So that's one of the goals I have. I know the conjunction. We know that there are 5 there. And for each one of them, I want to tell them it's in. How do I tell them it's in?
You could have the original example with just those 5 as ones, and then have the subsequent 5 examples, each of those removed, yielding zeros.
Okay, so let's take this. So this is a pre-step. You're saying, first of all, let's tell them what's not there. Right? How do I tell them what's not there? I'm going to give them an example that covers what's there and put zeros on all the others. Immediately you know that all those that have zeros in them, because this is a positive example, they cannot be there. Right? So immediately I narrowed down from 100 variables to a smaller subset of all the things that you really have to focus on. So I'm going to take this suggestion and give you an example that has x2, x3, x4, x5, and x100 on positive example. again, you should convince yourself that immediately you know that x1 is not there, x2, 3, 4, 5, 6 is not there, everything between 6 and 99 are not there, because it's a monotone conjunction, I told you that too, and therefore you have a subset. Now that you have a subset, what will you do? Yeah? Go to the same procedure that we did before, basically show you that each one of them is needed, each one of the subsets. So now we learn a superset of the good variables, and now to show you that all these variables are required, I'm going to do the same thing as before, right? I'm dropping x2. The example drops from a positive example to a negative example. You see the label is on the right, which indicates that I need x2 and so on. Need x3, and we can continue this way. Up to need 100. How many examples are needed? 6 examples. A lot less than what we had before, right? And again, we learn exactly the function. Yes?
In the previous one that was proposed, where instead of starting off with all the ones that are correct activated, you just give them one at a time. So you say everything is 0, wouldn't that be... Sorry, would you say everything is 1, and then x2 is 0, everything is 1, but x3 is 0, so on. Isn't that only 5 instead of 6? And you get the same information at the end.
You wouldn't know that some other variables.
Okay, so speak up.
So you wouldn't know, for example, that x7 isn't needed.
Right, so you basically know that these 5 are needed, but you don't know that something else is not needed. Because it was on in all the positive examples that you showed, maybe it's needed. So this example that we showed as the first one, but you also can show it somewhere else in the process, is required in order to show that not only these are needed, these are the only ones that are needed. So I think in this specific case, a simple case, probably we cannot do with less than 6. Okay, so first of all, what I wanted to show you here is the teachers are needed. It saved you a lot of time, right? Only 6 examples as opposed to 100. So that's one important lesson. Now, it's important to realize that actually modeling, teaching, really formulating the problem as a good problem is a little bit tricky, because we kind of defined hand-wavingly what is allowed in the interface between the teacher and the learner. And what I said is that the teacher is allowed to give examples with their labels. The teacher was allowed ahead of time at the beginning to say, the hypothesis space is that of monotone conjunctions. This was also important. But you could envision probably a situation where the teacher is colluding with the learner, and basically they kind of encode somehow the hypothesis class, the hidden function. The hypothesis class, the hidden function in the interaction, and then the learners gets it and knows exactly what the function is. So it turns out, people have worked on it, that sometimes modeling teaching is tricky. Nevertheless, it's another way of learning. So basically, the goal here, or one of the goals in this game that we're playing, is to illustrate to you that there are many ways to formulate learning. And the standard one that we're going to spend most of the time in the class on is not necessarily the only one. But we're going to move back to it. So now the question is going to be Protocol 3. In Protocol 3, nature generates examples. Someone labels it. And the question is, how do we learn? Right? So basically, you don't have control on the examples. You just observe them. The only thing you have control on is your learning algorithm. So I just sampled some examples here with their labels. So all ones is a positive example. 1, 1, 1, all the rest 0 is a negative example. And then a few other ones, 1, 1, 1, 1, 1, a few zeros in the middle, 99 and 100 are 1. This is a positive example. I wrote the target function on the top there, so you will remember and agree with my labeling. So that's a third learning protocol. How would you learn? Yes?
You could start by looking at all the positively labeled examples, and anything that's a 0, you know, can't be part of the conjunction.
Okay. Suggestion here is to really focus on the positive examples. In a positive example, if a variable is 0, for example, x15 is 0 in a positive example, because we know that we are after a monotone conjunction, x15 cannot be part of it. Everyone agrees? Okay, good suggestion. What else? Yes?
I guess you have to think a little bit about, is it random which switches are flipped on and off?
What do you mean? Is it random? What is random?
Like, do you have an equal probability of getting 0 followed by 99 ones as 99 ones followed by 1 0? Or is there some kind of structural element about which switches are getting flipped on and off so that you can learn which 0s are?
Okay, but maybe I'm misunderstanding what you're saying. The examples are labeled correctly here.
Yeah.
No noise at all.
Yeah, I understand, but I'm saying, like, you're essentially collecting information, and is it sort of uniform? Maybe that's not the right word, but like, are you collecting information at the same rate as you learn?
Okay, okay, I understand what you're saying. So you want to understand the X, basically. Forget the labels for a second. Do I only look at examples where X7 and X9 are always on? Or is it something in the distribution that, I mean, I'm not exposed to some parts of the space? Why do I care about this? Do I care about it? So let's assume, I mean, the space is 100 variables, which means how many possible X's are there? What is the size of the instance space? Everyone? 2 to the 100, huge, right? Of course I'm not going to be exposed to all of it. So if I understand your comment is, make sure or check whether you're biased. Maybe you're only exposed to this area in the space. I mean, you only look at examples where X7 and X9 are 1, and so on. But so think about whether you care about this. Yes?
This is tangential, but is the first example there enough to prove to the learner that there is a monotone conjunction?
Okay, that's actually, unless it's a trivial case, I think the answer is yes, right? Yeah, because it's a positive example where all the variables are on. Otherwise, it will have to be, if there was non-X7 in the conjunction, all ones will never be 1. Yes, so unless it's a trivial case, yes. That's not relevant to this learning algorithm, but a good point. Okay, but we have a beginning here, right? So there was a suggestion here already if we care about the learning algorithm. By the way, your point is going to be very, very important pretty soon.
When you try to see how many iterations you need to see before you
And it's going to be also important to provide us with confidence. We'll say something about it again in a few minutes. But for now, let's try to develop an algorithm. So we have a beginning of an algorithm. Basically, the point was, notice that positive examples are informative, right? How about negative examples?
I had a question actually. So there might be a case that the nature is not able to provide us enough examples to decide whether x100 or one of the literals is in the function or not. So how should we deal with that?
Okay, excellent point. So maybe nature does not provide enough example to determine whether x100 is in or not. Keep this example 5 more minutes, okay? We're going to address this. This is a really important example, a really important question. But let's move on with the algorithm. So we have a suggestion. So the algorithm that I'm going to use is going to be called elimination. And basically, it's going to follow the suggestion that you've made, which is if I know that something is not active, is 0 in a positive example, I'm going to kick it out. It cannot be part of my target monotone conjunction. And basically, that's it. That's going to be everything I need to do. So negative examples are not really going to help me here. So let's see. Let's do the details. So I start with all ones. I learn nothing, modulo the fact that it's a monotone conjunction. Now I have the next example, 1, 1, 1, all zeros. It's a negative example. Did I learn something? Probably nothing. Learn nothing. Here is a positive example. What did I learn from this positive example? That everything that is 0, everything between x6, I think here, up to x98, isn't part of it. So basically now I know that my target hypothesis, or my current hypothesis is going to be x1, 2, 3, 4, 5, 99, and 100. And we can keep on going this way. Here is another positive example where I furthermore eliminated x99. So I'm eliminating x99. So now I'm in with x1, 2, 3, 4, 5, and 100. I have another negative example, learn nothing. Another positive example that in fact I learn nothing from. Look at the one next to the last because I already knew this. So my final hypothesis is x1, x2, x3, x4, x5, x100. Okay? That's what I learned from this data. Yes?
It's not technically correct to say that negative examples don't give us any information, right? Because even if I had just a set of negative examples, I can still say something about the function.
What would you say? True. What would you say?
For example, in this case, the last third example, I can definitely say that at least one of x2, x3, x2, x4, and x5 has to be in the convention.
True. Right. So you do know something from it, only that I don't know how to use it at this point in the algorithm. So I agree with that. So maybe if all you had to do is deal with negative example, you will be forced to say something like this. Well, I don't know exactly what the function is, but I know some conditions about the functions. And this could be very useful sometimes. But now, since we have a good learning algorithm, we're going to take it. Question there?
Yeah, so I was wondering whether we can calculate the current as the possible one label and calculate each x1, x2 to x100's occurrence when one occur exists. So we can know like if the positive label is 50, we can have any labels that occur in 50 to keep them as the element of the conjunction.
So if I understand your suggestion, let's count how many times a variable appears with positive in a positive example. Is that what you're saying?
So let's calculate how many one exists in the positive label. So let's say we have 50, and from the conjunction we have x2 to x100, and we can calculate like how many times one experience. Let's say x2 has 5, or any times of the element should be larger than the positive label occurrence. So
Okay, so I'm not sure I get it, but you're saying you can look at the positive example and get an indication of how many elements are active in the conjunction. You're right. So basically, if you see positive example with only 15 on variables, you know that the conjunction must be smaller than that. And that's true. So that, again, is kind of like the suggestion here. There are probably other hints on the conjunction or the target function that you can draw from the data that we haven't used it. We basically used only the positive examples in a relatively straightforward way, not because there are no other hints, because one, this gave us a very clear learning algorithm. Two, it's sufficient for now. I agree that you can learn additional things. But let's stick with this learning algorithm. I don't know that the other hints are going to change the hypothesis. They're going to give me some additional information about the target function, but they're not going to change, at least I don't know, how to use it to change the hypothesis. That's the hypothesis that we can get from this data. You cannot get a better one. But let's now go back to your question here. So you ask, what happens if the data doesn't help us enough? Which is what's happening here, right? What happened? X1 was not eliminated. We think that the hypothesis is X1, X2, X3, X4, X5, X100. The real hypothesis is without X1. What are we going to do? Yes?
I mean, if there's no more data to be collected, that's why it's called a hypothesis.
It's a hypothesis. That's going to be the working hypothesis. But is it good? Is it bad? Is it, are we going to make mistakes in the future? So let's start with this. Are we going to make mistakes in the future? Let's assume you learn this, you take this, you go home, that's my function. Now I'm going to use it whenever I go and need to classify things. Is it going to be good? Yes?
You only get false negatives, right?
I'm going to get false negative. What do you mean when you say that?
So, I mean, the only of that fusion grid you'll get is false negatives.
Get whatever is positive and also whatever is...
Okay, so basically you're saying, if there is a positive example out there, you're going to be able to say that it's positive? No, okay. So what are you saying? Let's be clear. I mean, that's a very good point. So what mistakes will I make?
So, in the case where...
No, let's continue with this. That's a good thing. So give me an example of an example on which I'll make a mistake.
So if X1 is 0, the rest are 1, you'll call that negative when in fact...
Exactly. So if 2, 3, 4, 5, 100 are on, which means it's a legitimate positive example, but X1 is 0, it's still a legitimate positive example, I will think it's negative, right? So some examples that are positive, I'm going to say that they are negative. What about negative examples? Will I make mistakes on negative examples? Never. So I will only make mistakes on positive examples, but only very specific ones. So it's not good. Or is it good? What can we say about this?
Depends on the frequency of 1s and 0s. I mean, if it's truly random, you're going to make mistakes 50% of the time.
Right, so now we are going back to the idea of the distribution that you had and the idea, I think, on counting that you get. So basically, one line of thought that you can develop here would be something like this. I've trained on a lot of data. Not so much, but let's assume it's a lot of data. In this data, I've never seen a positive example with X1, 0 in it. Had I saw this, X1 would be eliminated, wouldn't stay in the hypothesis, right? So I've never seen it in my training data. This phenomenon of positive example with X1 being 0. So if my test data is sampled from the same distribution, I don't know what is the distribution, but there is some distribution, right, that generates this, that governs the generation of the example. So if the test is sampled from the same distribution, it's probably unlikely that I will see positive examples with X1 0. And therefore, I will not make mistakes. So that's going to be the type of guarantees we're going to develop. We're going to quantify it a little bit better. But basically, that's the key idea. The key idea is test distribution and training distribution are the same. We don't know what they are, but there is some distribution. And if there's something that was unlikely in the training, with high probability, it's going to be unlikely also in the test. We're going to do okay. That's basically what we're going to say in the next few weeks. So we're going to live with the fact that we cannot learn something exactly. When data is random, not everything is available to you. You're not going to learn the true function. So as opposed to protocol 1 and protocol 2, where we did exact learning, remember that I emphasized the exact. In protocol 3, exact learning is a dream, but we still want to be able to say something about how well we're going to do. Yeah.
Could the way you quantify or the way you rate this model be based on what metrics you use? Because it would have, because as you said, you only get false negatives, that would mean you'd have a high precision, right? But you'd have a low recall.
Mm-hmm.
Your recall would be lower than the precision. So if you base your metrics on precision, then you could, in your mind, would have a better model.
True. So basically what you're saying, it really depends on how I'm going to use it or what application I want to use it for. Sometimes maybe I don't care, because really what I want is I want to learn a superset of the function. Sometimes maybe I want to learn a subset of the function, so which means I care about one-sided error of one type of another, which is in practice correct. At this point, we're going to not use it. We're just going to say, is it the same as the function or not the same as the function, just so that we'll be able to say something about the probability of making mistakes. So basically, just to, I'm going to start with this next time, we really can go in two directions now. We can either continue to analyze this probabilistic intuition that I expressed now, with X1 being 0, not present in positive example in the training, therefore unlikely to be present also in the test. Or we can go with the algorithm. So let's just make the algorithm, the elimination or other algorithms that we talked, a little bit more rigorous and generalize this. So we're going to go in both this direction. Next time we're going to start with what is called here mistake-driven learning algorithm or online algorithms. And later on, once we understand this better, we're going to move to the top part, which is analysis of the probabilistic intuition. Final question? Okay, have a good weekend.
So is the reason why you would essentially apply like this sign function you were talking about earlier to the data to basically get it into a form that lends itself to like the conjunctive, like to a system of ones and zeros like we're doing here? Or is this more for theory?
Okay, let me try to understand. So you talk about what we did today, the example of the conjunction.
Yeah, the expressivity of conjunctions in general.
Oh, so conjunction are actually very interesting example. It's not just for theory. I mean, many
Right.
functions that you want to learn in life are conjunctions.
Yeah. No, that makes sense. But so if you have, say, every one of your variables was continuous, and you have this ability to flip 1 to 0, and compress your feature space in such a way. Like, is that basically why we apply this? If it's positive, it's 1. If it's not, it's 0 to our data that we were talking about earlier when you apply a sign function.
Oh, so that was in earlier where I took the dot product and then applied the sign function. That's because at the end, in many cases, I care about, is it positive or negative? Is it a cat or a dog?
Yeah.
Right? So true, the learn function, and we'll see it next time, is going to assign real value to examples. Okay, in conjunction, it directly assigns Boolean values, but in almost all learning algorithm, the algorithm is going to assign a real valued function. But in most cases, you care about a decision. Right? So I want to threshold it and say, if it's above this, cat. If it's below this, dog. Right? So that's basically what the sign function is doing. Now the sign function is doing it relative to 0. Maybe you want to do it relative to 0.15, but that doesn't matter.
Cool.
Yeah.
Thank you so much.
Hi.
A quick question for the conjunction.
Yeah.
So on the quiz, there was a question asking like conjunction x1, 3, and 4, and as is like linear function for that.
Yes.
So what's the trick for that? I don't quite get it.
So first of all, go to the lectures. I think the first lecture, introductory lecture number 1, we talked about this, and I gave an example. So first of all, do you understand what does it mean for the two functions to be the same? So basically what I want is that my input is zeros and vector of zeros and ones. Conjunction gives a value of 1 to some of them, value of 0 to others.
Yeah.
Linear function, same thing, gives a value of 1 to some of them, 0 to another.
Yeah.
And I want to find a linear function that behaves exactly the same as the conjunction.
Yeah.
So the trick is, first you have to understand this. So now, how to do this? You basically, in the case of conjunction, you put 1, weight equal 1, wi is going to be 1 for all variables that are in the conjunction, 0 to all the others, and you put a threshold of 1. Now, if you think about what is the impact of that, it means that, the threshold is going to be the number of elements in the conjunction. So 4, if that was the case. Right? So that means that when you do the dot product, because you have 1 on all the active variables, essentially the dot product is going to be the number of active variables. If this exceeds the number in the conjunction, you say yes, because it means that all of them are on. If it's below it, it means that at least one of them is not on. So it's not equivalent to the conjunction. It's equivalent to the conjunction. Did I get it?
But the question asked is like the conjunction rather than like the conjunction equals to 0, right? Sorry, the conjunction equals to 1, right? So how come we say the x1, 3, and 4 are larger than?
So I have a conjunction y equal x1 and x3 and x7.
Yeah.
Let's say I have 10 variables. So I can write a linear function. So what I want is I want a w. And I need the theta also. Okay? So basically what I'm saying, if I'm going to take W1 equal 1, W3 equal 1, W7 equal 1, all the rest are going to be 0, and theta is going to be 3, this function is going to behave exactly like a conjunction. So if you take dot product, it's going to be completely equivalent to this function. agree?
Yeah.
So if you take a positive example here, it's going to be positive here. If you take a negative here, for example, if you take x1 and x3 are on, all the rest are off. It's a negative example for this. It's going to be a negative example for this too. Do you see that?
Yeah.
Okay.
And so how would you draw the monotonic conjunction function?
What do you mean draw?
So what would be the function? What would not be a monotonic conjunction?
Oh. X1 and not x2.
Okay.
That's not monotonic.
Okay.
Right? So this function, if you draw it this way, so you have x1 and x2. So if x1 is 1 and x2 is 1, the function is going to be 0.
Okay.
Right? If x1 is 1, x2 is 0, function is going to be 1. And this is going to be 0. That's a non-monotonic
Okay.
conjunction.
Does the monotonic actually means the trend of the slope?
Okay. So ask me this question next time
Okay.
in class.
Okay.
It's a good question.
Okay. Thanks.
Yeah.
Follow up with the conjunction. The first example, considering this disjunctive also behaves in this way.
If it was a disjunction,
It also behaves in this way.
you can modify the learning algorithm a little bit and it will learn disjunction concept.
Yeah,
If that's the
because
question.
someone asked before in class that this proves without conjunction.
Oh,
but
no,
I
no.
didn't
The
know.
question was, does this prove that this is a monotone
monotone.
function? And I think the answer is yes. Because if this is a positive example, it cannot have a negated variable in the disjunction.
Oh, I see. So it's a monotone conjunction.
Yeah, so I think the comment was that because 1, 1, 1, 1, 1, 1, 1, 1 is a positive example, and I told you it's a conjunction, it
Okay,
must be a
it's a
monotone
monotone,
conjunction.
okay.
It cannot have negations.
Okay. Okay, I also have a question with the C. So the small n here is a number of examples?
No, n is the number of examples. Yeah.
So why when k like goes to s, like if k equals to n, you only have like one example to test on?
No. Yes, but you have to do it n times.
So like every time you only test on one example.
Yeah,
is
but
that
you
like
have to
two
train. But you have to train n models.
So it doesn't matter like each time you only test on one example.
Yeah, but the training is the costly part of the process.
I mean, like, is that really good? Like every time you only test on one example, although you have a
This
good
is,
model?
as I said, this is actually a process that is called, or you don't have it here, you have an old version of the slides, but it's actually a process that is called leave one out. Yeah, sometimes people use this if they don't have a lot of
really?
data. Yeah. So it's costly because you have to train a lot of models.
Yeah.
But again, all these questions are really good questions. Why didn't you ask it in class? I mean, I should answer to everyone.
Yeah, I have to the next step.
Yes.
Thank
Yeah,
you.
I asked it, but I want to explain it more
Okay.
specifically. So in class, what I asked is we can calculate the sum of the one experience.
The
There would-
labels.
Yeah, there would be two, and any time that is, we calculate one, so there is three, 2. We can keep anything that larger than 2 because the condition is when the element exists. And then we can eliminate anything that's smaller than 2, so we can do it
Okay,
at
just a
once.
second. So you suggest another algorithm.
Oh, yeah. Oh.
Let's see. So
So
you're saying basically what you did is you counted the number of positive examples.
yes. So there will be 2, and we calculate the x2, x1, and we calculate the 1.
Okay, and basically what you're saying, a variable that is in the conjunction has to be on in all the positive examples. That's what you're saying, right?
Yeah.
That's your intuition. I mean, you didn't articulate it this way, but basically your point is, if a variable is in the conjunction, it will be on in all the examples,
Yeah.
all the positive examples.
Yeah.
And therefore, the number of times it's on has to be greater than the number of positive examples. All those that are smaller than 2, I can eliminate.
Yeah.
I think you're right.
And
This is an alternative algorithm, and it will give the same results. Good. I mean, I didn't get it from your comment, but now I understand what you're saying.
And it will be faster because once we get these 3 labels, and we can starting from 0 and eliminate the element very quickly.
Yeah, I think it's kind of equivalent in terms of efficiency, but it's an interesting way to think about it. So again, let me try to say it in a cleaner way. Tell me if that's what you mean. So basically you're saying, I know that a variable is in the conjunction if and only if it appears on in all the positive examples. And therefore, if I count the positive example and then I count the number of on times for each variable, the variables in the conjunction have to have a number that is larger or equal to the number of positive examples.
Yeah.
And the rest I can eliminate.
Yeah.
You're right. It's good. It's a good algorithm.
Is it?
Yeah. Okay. So it's another
Is it similar?
perspective. I think it's equivalent, but it doesn't matter. It's a different way of writing it, which is nice.
Is
Okay.
it similar to protocol
Two?
3? Is
Yeah,
it similar
it
to
is protocol 3. Yeah, it is protocol 3. And it's I think it's equivalent to the algorithm that we gave, but it's another way of saying it, which is